Excuse me, ma'am.
Yeah.
Before you continue, I have few doubts from the previous class. Um, Actually, it's
Okay.
instantiation and feature tuning, least square regression line, and cost function. These are the
Mm-hmm.
three doubts I have from the previous class. Could you please brief me for that?
Tell me, you have to ask the questions for that. What exactly you have doubts?
Okay, I couldn't understand it actually. I
Did
don't
you go
have a
back to
specific.
the recording?
Yeah, I have gone back to the recording. I have seen that.
Okay, so is it possible that I explain you at the end, or others also have got a doubt?
I have only one question actually regarding
Yeah.
this scaling.
Tell me.
Yeah, so in the transformations you mentioned to create new features using the existing, maybe via linear equations or any interoperations, right? So if we are creating a new feature using the existing, which are themselves going to model, is it still going to impact or how would it impact the model performance? Because the information is already there with the existing, right? A or B feature, right? So A multiply B, why would it impact the model performance?
See, we do that only in case when we have very less number of features. So we can increase the dimensionality of the features by performing those interaction. That is not an ideal situation. Ideal situation is you should get more number of data. I mean, you should define more number of features and actually get the data for those features. But in any case, if you cannot get the data and you cannot define new features, this is one way you can try and see if it is improving your model's performance.
But this does not guarantee or kind of
No,
may not have an impact on the performance.
no, no, no. So a feature interaction can be very meaningful. I think I had taken one example. Say housing price prediction problem. Say you have number of bedrooms, but number of bedrooms in 2 BHK house will have a different. I mean, 2 BHK and 3 BHK. There's a difference in the rate price of the house. But 2 BHK in a city and a 2 BHK in a village will also be different. So rather than considering 2 BHK as an independent feature, you can create another feature which is a combination of location and the maybe latitude, longitude, or something like that, or a location, indirectly location and the number of bedrooms. So that is a feature interaction we can create by multiplying two features, the latitude and number of bedrooms. So that way you can have more meaningful representation. That is one way of looking at it. You know the domain knowledge, and like in this case, we know that 2 BHK in one city, 2 BHK in another city may not be the same rate. So that way, feature when you create another features by performing some transformation on the original features, it will help. The other reason I said you have a less number of features and you cannot get new data. Then you can try by taking uh, the polynomial degrees of the existing features and different uh, operation like x1 into x2, then x1 into x2 square and all. It might help. Okay. So last class here where I had stopped, I'd explained what is a cost function, why you need a cost function. Okay, why do you need a cost function? Why are we
To
defining the
find
cost function?
parameter,
Sorry?
to get the best values of the parameter.
To get the best values of the parameter. So cost function, sometimes also known as a loss function. And basically we use some mathematical operation between the actual value and the predicted value. So what is h of theta x here? Yes.
Hypothesis of x function with
So
x.
So it is nothing
X
but
are
a
the
predicted value.
independent variables. Yeah.
Hmm. So it is a prediction, basically. So we are trying to find out the difference between actual value and the prediction value. Now we are trying to find out this difference. We can use any mathematical function to capture this difference. So here we are using mean square error. Mean you are taking by like dividing by number of training examples. That's a mean. Then we are taking summation, and then we are taking the square. So it is sum of square error, and then we take a mean, it becomes mean square error. That we are taking as a cost function to decide that how much our actual is, how much our predicted value is deviating from the actual. And I had explained this intuition that if our actual, where that figure has gone. Yeah, this is a case. If our actual, so this crosses our actual, and this we have come up with a regression model is this line. So our predicted values are deviating from the actual. So that intuition we are capturing in a cost function. And then we plot this second graph, parameter versus this cost. What we get, as you can clearly see, the cost is increasing. So likewise, for a different values of parameters, we will get a different cost function. Do you agree on that? The different values of parameters will give you mathematics. It's a simple mathematical equation. The only variable thing in this cost function are the parameters. So different values of parameters, we can get a different cost function. Do you agree on that?
Yes.
This is the cost function where n is number of training example, they are fixed. Y is the actual value that is fixed. This hypothesis function. It is what? What is the hypothesis function for linear regression? Yes. Summation of theta I into xi, correct? So I can replace that hypothesis function here in this place. What is a variable in this? X is also something which is given to us, which is there with us. We cannot tweak with X, we cannot tweak with Y. The only thing that we can change is the hyperparameters, thetas, parameters. So we are plotting this cost function only with respect to theta versus j of theta. And when we change the parameter values, theta values, we get a different cost function. And just plotted this graph. Why? Because this is very significant. The shape of this graph is very significant. I mean, it is looking perfectly inverted ball, but yeah, you get somehow somewhat similar. Somewhere something like this, something like this. The important is this is a convex function. Our cost function is a convex in nature. So again, I'm not sure in mathematics, have you come across this convex functions yet? Convex functions and concave, or
No.
simple.
No,
Yeah. Okay,
no,
but
ma'am.
simple meaning of convex, are you aware what is concave and convex? Everybody has learned in physics. Convex, concave, convex mirror, concave mirror.
Convex will have one minimum, two maxima, and concave will have two minima, one maximum. Is that the one?
No. Okay, I'll explain. But convex is something you can relate with this shape. This is convex. This is concave, right? You can relate with that. The shape is convex and concave. Okay. Okay, before I go ahead with this convex and concave, a simple recap. What is a gradient? Are you aware of what is gradient? Or what is the meaning of derivative? Interpretation of derivative. Are you aware of that thing?
Rate of change.
It is the rate of change. So say we have some curve. This is my hypothesis function. Curve just taken so that we can visualize it clearly. At certain point, we are taking a tangent to that point. What is the slope of that tangent? Is nothing but a derivative of a function at a point x. This is how we define slope. So if we have a slope of that derivative line is this way, we can say it is a derivation, or you can say it's an increasing direction. When we have slope something like this, we call it is a decreasing direction. So ultimately, between a function, this blue curve, you can call it a curve of a function, any function. And at this point of x, we are drawing a tangent line. And then slope of that tangent becomes the derivative of a function. This is that blue line. Some function with which this blue line is drawn. We take a derivative of that function at point x. This is interpretation of a derivative. Now in this example, we have just one function x, one feature x and corresponding f of x. What if we have two variables? So we have this function of two variables. This is some example of a mathematical function. x square y sine of y. And then I want to take a derivative of this function. So there comes the concept of partial derivative. So do you remember what is partial derivative? All forgotten?
Yes, ma'am.
Okay. Here you don't, I mean, you will learn in maths class and you have to again remember everything. But whatever is required for this explanation, I will explain. So what do we do? For if we have just one variable, so we take like derivative of this function with respect to that variable. This is our standard way. You can call it as y of f of x. So we can write dy by dx. Now this should sound similar. But when we have two functions, two variables, x and y, our function consists of two variables. So we take a partial derivative. Why call this? This is a special DAO symbol for a partial derivative. This symbol. It is a partial derivative of this function. First with respect to first variable, second with respect to second variable. Now you have to use a derivative formula. Well, you don't remember because you don't remember what is derivative, what is partial derivative. So you will definitely not remember formula. So go back, refresh your calculus, only derivation part. No need to go understand integration here. And then this x square plus this entire, it is very important that you understand at least the basic derivative formula. Otherwise, a lot of things you will not understand. Lot of derivation you will not understand. So this part, if you take a partial derivative of this equation, x square plus y sine of y. First, with respect to x, the answer will be 2xy. Now, how it has come, you have to understand, you have to remember the formula, which I cannot teach all the formulas. So just go back and find out yourself. How come partial derivative of this function with respect to x is 2xy and partial derivative of the same function with respect to y will be x square plus cos of y. This is an exercise for you. Go back, open your derivative, just Google it, get a derivative formula and find out how can you get this answers. You should be getting this answer. Now, what is a gradient? These two partial derivatives, if we put together in the form of a vector, then it becomes the gradient. So I can say derivative of f with respect to x is first component of a gradient. Second is derivative of x with respect to y is a second component. Then we are taking this in a form of a vector. Then it becomes, this is a symbol of a gradient. This reverse triangle is a form of a gradient. We say that this is a gradient of a function written in this way. And the first quantity we just calculated, it is 2xy. Second quantity we just calculated this one. And the original function is this one. And this again, this is a symbol where we need to calculate a gradient of this function. Gradient, that means how many variables you have. For individual variable, you will take a partial derivative with respect to gradient. This is very, very important that you should study and come back. Next class. Here also a lot of concepts will rely on your understanding of how to calculate the partial derivative, which is probably grade 9 or grade 10 maths. I know you have forgotten. So the time being, I'm explaining you whatever I can explain, but it's a simple formula based concept, nothing difficult. You just need to recall the formulas.
Madam,
Okay,
in the previous
yeah.
thing, here you
Hmm.
just found the slope of
Hmm.
that curve at a particular point, right?
Point, yes, that's a tangent point. Do you know what is tangent? Do you
Yeah,
remember? I mean,
yeah,
no,
yes,
no,
yes,
I cannot say,
that's
but
clear.
remember. Yeah.
Yes, yes, that's
Okay.
clear. I just check.
Okay.
That slope at that
Hmm.
particular point is what? Okay.
Yes, yes. Now say this red line is the curve of my function, some function. Why this example is taken? Because that will make you understand what is maxima and what is minima. So the positive side we get, say this is a point of maxima. These are the 2 points of maxima here. And we have 1 point of minima. So for the concave, this is a concave function. I can say concave curve. And this region is a convex region. For a convex region, we always get the point of minima. For concave region, we always get the point of maxima. And there are function which has got both maxima and minima, like this function. We have got both maxima and minima as well. The other point of observation over here, how many maxima do you see in this example? We have 2 maxima. But which one is having the higher value in terms of its y scale? The first one, right? So it is possible that for any function, it can have many maximas and many minimas. Like for the maxima, which is having the highest value, we will call this as a global. And here the maxima, which is having some lower value than the highest one, we call it local. So similarly, we have the local minima also as well. We can also have a global minima. Okay, so this is a concept. The another thing, what do you note here? This is a tangent point. This is a point at which I've drawn this tangent. What is the slope of this tangent?
0.
0. You don't find any rate of change. Similarly, at this point, the slope is 0. At this point, the slope is 0. So very important observation. At the point of maxima or minima, the derivative of that function will become 0. Again, a very important result, a very important observation that we will use it in further derivation. Okay, now let's relate with our problem of linear regression. Suppose we have this car price prediction problem. So this is Y. And for a simplicity, say we have just one feature, mileage. So based on this feature, we have to predict the car price. You can see three different equations. So here something like Y is a car price is equal to, say, theta 0 plus theta 1 into mileage. So that is X. Theta 0, say for the simplicity, it's a bias term. We'll take it as 1. What you see is varying in this three equation. What is varying?
Parameters, theta.
Parameters are varying. So if we change the parameters, we are getting three different equations. Theta 0 also can vary. So how many values you have for theta 0, those many number of equations will increase. But that's not a point that I'm trying to show. Let's concentrate on theta 1 now. So we are changing one parameter value and we are getting different equations. When I say different equations, that means we get a different car price for the same example. Let's take one mileage example. These are the training data points. So 1 point, second data point, third example, and the fourth example. Like that, we have 4 examples. You can plug in only any one combination. Say plug in 9.8. Say here you take mileage as 9.8, 9.8, and 3 different points you will get on the curve. Those 3 different points are plotted in this curve. So this is a first point plotted, first equation. Then this is the, say, point plotted for the second equation. And then say this is a point plotted for, say, third equation. So in this, and how are we getting three different points? Yes. How are we getting these 3 different points?
Different theta.
By different parameters. Yes. So 1 point at okay, one more thing. This is weight. So this is theta versus j theta. So we are actually not directly plotting a hypothesis, and this is a hypothesis function. See, we are calculating error, and for the simplicity, it is plotted over here. The parameter value, which is giving you the point of minima. This is a point where we are getting the minimum value. Those minimum values are coming from which equation? Second equation. That means the parameter values, optimal parameter values are theta 1. For the theta 1, it is 0.25, and for theta 0, it is 1. Because at that point in time, we are getting the minimum value. Now, what is other observation? You have so many different minima.
Madam, one question, madam. How to know that 0.25 will give the result to the minimum, global minimum?
No, we don't know that. I'm coming to that. 1 minute. In this, that's what I answered second question. Just wait and let me complete this concept. We have so many point of minima. How do we know this is a local minima or a global minima? Now try to relate with our linear regression cost function. This was just some function plotted. So do we have many minima or many maxima here? Or we have just one minima? The nature of the nature of the cost function that we have chosen, which is a mean square error, has got, I mean, this is another reason why the mean square error is chosen as a cost function. It is a convex function. That means its shape will always be convex, and any convex function will have only one minima. So that problem is solved. That how do we know, how do we ensure it's a local or a global minima? That problem is absolutely solved here. That is a case of linear regression. Even we will see the same concept will apply in case of logistic regression as well. The choice of cost function is such that the cost function graph that we will get will be convex in nature. And this is a definition of convex, mathematical definition of convex. So for any curve, if we take any 2 points on the curve and try to draw the line, that line is the interior of the curve. But with a simple understanding, you can say this is whenever we see this kind of shape, it's a convex region. This was a 2-dimensional example. Now suppose we have 3-dimensional. Our theta 0 is also varying, theta 1 is varying, and then third dimension will be y-axis will be j, that is your cost function with respect to both the parameters. So this is the graph of 3-dimensional. Up to 3 dimension we can visualize. So we have taken only example of one feature and one bias term, and here both the parameters are changing. Theta 1, theta 0 both are changing in the error surface. So this is the plot of error surface. We call it, this is the error surface. And at different point, at different point of graph, wherever you see, we will get a different value of theta 1 and theta 0. Say suppose we have this kind of the error surface. Again, the importance of the cost function that we have chosen for linear regression. Say here, how did we start? We assume certain value of theta 0. We started with theta 0. Sorry, we assume certain value of theta 1. We started with 1. Then we are changing. We can start from any value. We don't know which one value will be the accurate one. So randomly, all these parameters are initialized with any values. Generally, for this machine learning, basic machine learning algorithms, they are initialized with 0. So you can, but it can be initialized with random values, and then we are changing these values so that we are coming up, we are coming up with the line which is correctly approximating the given data points. So that point again, I'll talk here about that. So we can start with any random values of theta 0 and theta 1. So this is the value of theta 0 and this is the value of theta 1 that we have started with. Then every step, we are changing the values of theta 0 and theta 1, and then we are moving towards the minimum. May not necessarily it is a global minimum, but yeah, we are moving towards the minimum. Now you can imagine this is like a hill. You have a hill and there is, I mean, 2 hills and there is a valley in between, and you're trying to throw the ball down the hill. You want to make sure the ball should rest at the bottom of the valley. It should not bounce back again and come up again. So how will you ensure that? You want to give a push to a ball such that it will initially the speed will be faster, and then in every step the speed should be reduced so that it will rest at the bottom of the valley. This is something like this. You're starting somewhere from the top, and then at every step you want to give a push such that it should rest on the bottom of the valley. But here, this is a function, there's an error surface which is not convex. So once we start from here, we may reach to this valley point, or we may reach to the other valley point. We know this is a point which has got a global minima. This is a point which is a local minima. And there is no way to tell that when we are starting from this point, which way the ball is going. But here, in case of linear regression, we don't have to worry about it. The choice of a cost function is such that, and it is always giving us global minimum. There's just one value. Okay. Now, still I'm continuing with the concept, same concept ahead, which will lead to a algorithm known as a gradient descent. So again, take this 2 hill and then we have a valley in between. You want, am I audible?
Yes.
Good.
Mhm.
Yes.
Okay. You want to push a ball from the top of the valley. That means ball is descending. And then that your push should be such that it should rest on the valley. So hence the word here descent. And what is decreasing? So that's what I'll explain. First, let's understand this intuition. The left hand side we have size fit square. That means we have this x. And on the right hand side we have y. Just example of price prediction, housing price prediction, and just one feature. And various value, and what you see, the cross points are the actual data points. That's our supervised data point which is given to us, and we are plotting them. Then we have to draw the hypothesis function, which is our this hypothesis function theta I xi. In this example, we have just one, so theta 0 plus theta 1 x. They call it x1 for simplicity. Now we have chosen some values. So say initially theta 0 is being chosen as say minus 900 and theta 1 to be chosen as minus 0.1. Random values, initial values. And you can see the line when we are plotting is a blue line. Is it anywhere near to the actual plot of a data that we see? Obviously, we can see no. So at this values of thetas, if we calculate the cost function would be very high. So on the right hand side, on the x-axis, we have theta 0. On the y-axis, we have theta 1. And the contour lines that you see, rather than this three-dimensional here, this is a three-dimensional graph. We can visualize this in a two-dimensional graph using this contour plots. So if you want to understand what are these contour plots, refer to Khan Academy. Videos are there for a quick understanding. Khan Academy videos, and there is one more site, 3 Blue 1 Brown YouTube series. They are also very nice to understand basics of calculus, linear algebra, very quick intuition. We want to have the intuitive understanding. So what are the contour plots? That is explained in this. Any higher dimension plots we can visualize using the contours. So this is the contour plot example. And how are we drawing this? This is the plot of cost function. Now, so this is a point that we are getting in this contour plot when we have this choice of theta 0 and theta 1. Cost is very high, yes, because we can clearly see this blue line is nowhere near to the red dots. But initially we don't know which are the good, which is a good fit line, which are the good parameters. So when we code it, you have to pick up any random values. In the next step, we change the value of theta 0 and theta 1. So we are changing the theta 0, some other values we have come up with. You can see we have changed the orientation of the line. We have reduced a cost a little bit. Third iteration, now I'm using the word iteration. It's a simple step. We have further changed the value of theta 0 and theta 1. And we are further changing the hypothesis line and calculating corresponding cost. A little bit we have seen improvement in the cost. Fourth iteration, we are changing a little bit parameter. Orientation is changing. Fifth iteration, sixth iteration, seventh, eighth, ninth, and probably after ninth iteration, we are getting a line where our cost is minimum here. We have started at some values of theta 0 and theta 1 here. Minus 0.1 and maybe minus 1000, some values, 900, we have started with that. And then at every step, we change the values of theta, recalculated the cost function, and we are observing that every values of theta, it is our cost function value is increasing. And then we have reached to the minimum value. So we cannot do any further improvement. And for that particular cost function, this is the regression line, or this is my hypothesis function. I'll call it regression line, or I will call it this is my model. Cost is there. I'm not saying it is 100% accurate line. We cannot get 100% accuracy when we have a very diverse data points like this. You can clearly see we cannot pass a single line from all of these data points because they are non-collinear. But we have come across with the best possible model, and for this best possible line, you have to pick up the which values of thetas are giving you this regression line. This is what known as a machine learning model training using gradient descent. Now, whatever I've just explained intuitively, we have to put it in a mathematical form. So that's what is a mathematics. We are initializing any theta parameter values. Then we are running this equation in every iteration. The new values of parameters are calculated. Old values of parameters minus learning rate. I'll talk about this alpha in a while. Multiplied by partial derivative of this theta, partial derivative of the cost function with respect to theta. Every iteration, what we need to change so that we reach to the minimum point. So rate of change, here we can only change the thetas. We cannot change anything else. So we are taking partial derivative with respect to theta. But what partial derivative? This is a cost function surface. This is a plot of a cost function. So we are taking a derivative. We are observing the rate of change of a cost function with respect to theta. So this becomes the gradient descent equation, a very important gradient descent algorithm, very, very important. The alpha, what is the learning rate? I'll explain. So this is a constant that we have added here. First, let me complete this gradient descent algorithm. I have few more slides to get better intuition behind this. So how we started? We started with some hypothesis function. That's what we defined for the linear regression. Then we have defined the cost function. Now our objective is to get the minimum value of the cost function to reach here, bottom of the valley, by changing the parameters values. That's what only we can change. So here theta 0 and theta 1. So we are starting with some random values, keep changing these two values so that it can reduce the cost function. And we hope that we are reaching to some minimum. You can say I gave this ball example. You are throwing a ball from the height, and then initially the speed would be very high, and you can see it is some curve. So towards the end, the ball is taking much smaller steps. This is what is this analogy we will again use it, the steps. So you can see this is a larger step size, and as a ball is approaching the valley, we want to reduce the step size so that ball doesn't doesn't overshoot the bottom of the valley and go to the other side. Again, a very important concept. How can we reduce steps like this in every iteration? So this alpha learning rate is for that purpose. This learning rate will help in reducing the step of the step at every step. In every iteration, this ball is reducing its speed. In other words, in every iteration, how much value we are changing for those parameters. That is what is being controlled by, you can say, this alpha. Okay, let's take this intuitive example first. Okay, we want to minimize the cost function. That is my objective function. We write something like this. We want to minimize a cost function with respect to what? Theta 0 and theta 1. So we need to find the minimum values of theta 0 and theta 1 so that we get a minimum value of this cost function. Right now, just concentrate on theta 1 because I'm visualizing only two-dimensional plane. So we are plotting theta 1 versus j of theta 0 and theta 1. But here we are only changing the theta 1. Initially, we have started with some random value, say your green dot, some random value of theta 1. And then we are applying the mathematical gradient update. We call this as a gradient update step. The new value of theta 1 equal to old value of theta 1 minus learning rate into partial derivative of this cost function. Okay, so this is a theta 1 value. And Why this partial derivative? What is the significance of this partial derivative? It is at this point we are taking the tangent. What do you observe for this tangent? Is it positive or a negative?
Negative.
Negative.
It is increasing.
It's positive.
Yeah, the line you can say it is increasing slope. So it is the positive derivative. Derivative is the slope at this point, and at this point you can see the slope is increasing. So at this point, this partial derivative will be some positive number. So you can now what do you understand by this equation? The new θ1 should be smaller than the older one or the bigger than the old one. Say alpha is a value which is less than 1.
Small.
Alpha is, yeah. Because what we are doing, the old value, we are subtracting some number. And alpha is less than 1. So it won't affect whether this will become negative or not. It is less than 1. So at this step, when we are at this point, our derivative is positive. That means our gradient update rule will decrease the value of θ1 by a certain value. So decrease is going in which direction? You can see it is going in left direction. So we got some new value of θ1. You can see this is a step we have taken. At this point, earlier we started with this point of theta. Then in first iteration, we have taken this step and we have got a new value of theta, which is definitely lower value than the previous one. Now I have explained how it is. This equation is appropriate because are we going the correct direction or we are going in opposite direction?
Correct direction.
Because we have to go to reach to the bottom of the
Minima.
valley.
We have to go to minima.
We're going to the correct direction. So old theta, and now we have come very correctly with this equation, we have come to the new theta. Okay, now say another example. Let's say rather than we are starting theta on the right hand side, we have picked up some random value here in the negative direction. It's a random initialization. So that is the initial value of theta. Slope at this point is a derivative at the point of θ1. That's what we are taking here. Derivative of this function at the point θ1. So what is the slope? Is decreasing, it is increasing. It's a negative slope. So that means that's a negative. No, it's a negative slope. After
If
this
we
point,
start in a negative point, then we have to decrease the slope.
So it's a negative, the slope is decreasing. That means the derivative is negative. And we have to reach to the bottom of the valley. So which direction we need to change? Towards the right. But the slope is a negative. Now see mathematically how it is, we are able to justify. So this is a negative derivative. Alpha is any constant less than 1. And we have this negative number. Negative becomes positive. That means now new theta will be greater than old theta. Can I say like that? Yes.
Yes.
Because this is minus and minus negative number. So minus will become plus. So new theta is greater than old theta. So now this is the old θ1. And θ1 will increase by a certain value. So we are going towards right hand side. We got a new θ1 value. And this is a step that is being taken. This is a step size for this iteration. Old theta and this is a new theta. And again, you can check, are we going to the correct direction? Yes, we are going to the correct direction, bottom of the valley. So no matter which value thetas are initialized to, this gradient update rule will take us to the minimum in certain iteration. How many number of iteration? We don't know. But yes, in certain steps, we will reach to the bottom of the valley. Okay, now we have reached over here at this point. Now we have to see, whether we have reached to a minimum or not. This is one way of saying that. At this point, what is the slope?
0.
0. So derivative is also 0. So what will you observe any change in new value and the old value? There won't be any change.
No.
So when we see this, that our thetas are not changing, we can consider that we have reached to the minimum value of cost function. This is one of the convergence criteria that, how many iterations we should run. We don't know. Either you can come up with, okay, maybe run for 10 iterations, 100 iterations, or when the thetas stop changing, that time you can stop your number of iterations.
So sorry, ma'am, one quick question, right? So what is the objective we are trying to achieve? I mean, so just like coming to the zero value, or like, what is the objective we are trying to achieve here?
Justifying that this is the correct gradient descent. How this gradient descent algorithm, this is a gradient update rule, is helping us to reach to the minimum. So this is intuitive understanding of this gradient update rule.
Okay, reaching to the minimum, right? So
yes.
Okay, so now let's say, I mean, this is some formula, right? And with the help of this, a certain calculation, we are reaching to the minimum. So now what is it indicates actually? I mean,
why we are reaching to minimum?
Yeah.
Did you attend last class?
Actually, last 30 minutes I could not attend.
No, that's where actually I had explained this intuition. Any other, everybody, are you able to understand why we need to reach to the bottom of? That's what I explained in the last class. Yeah. So when you come to the next class, it's okay if you're not attending, please go back to the recording. Every class is on top of the previous class. If I have to keep on repeating for everyone who are missing it, we won't be able to go forward. So either you can stay back after the class and ask whatever you have a doubts. And if I have a time, I'll explain you after the class. But for every single person, if they say that I missed so much, you explain again, you tell me, will I be able to go ahead in the class? So recordings are for that purpose. And when you come to the next class, at least listen once and come to the class. Otherwise, you won't be able to find any connection. Every class, there is a precedence on the previous class. So what is the significance? Why we are going here? Again, I'll explain at the end. So let the other class, we can go ahead. Is that fine?
One question I had.
Yeah.
So once our this loss function is 0, our model kind of receives either a line or for simplicity, let's say a line, right, which is giving us the best possible predictions. But even those predictions will have some offset as compared to the actual values. So when a new, like, right, this blue line, right, it is still having some offset to the actual value. So whenever a new data set comes for prediction, does our model tries to put the prediction on this line or on this line plus of average of that offset which is there compared to all other existing training data? What would it be?
Okay, 1 minute. It's a good question. Okay, so prediction. So this is a line. What is the significance of this line? All those cross data points though we have already with us. So we don't perform prediction there, right? So new data point is coming. So what we do, say here, some new data point which is not plotted anywhere. Say, let's say this is a size in square feet coming and I want to predict the price. So we have this line. I'll go and find out what is its projection on this line. What is the corresponding y coordinate? That becomes the prediction.
So do not I try to add the average of the vertical offset?
No, those are the errors. Vertical offset, if your data points will change, no. Vertical offsets are just the errors that will help us in finding out, evaluating the performance of this model. We don't add it. This is a mere prediction.
Right. In another way, I can say that whatever predictions during training I had made on this blue line, my actual points are vertical offset times away from the actual prediction, right? From the prediction made by model, the actual points. So should I not add that also?
No, you don't know that. What will you add in that? See, this is the actual, this is the essay. You have a test point. Oh, sorry, not test point. You have some unseen point. What is a vertical offset? To calculate the vertical offset, you should know the actual y.
Right.
Do you know the actual y? When it comes to new unseen point.
Average actual offset from training data, I know, right?
No, we don't do like that.
Okay.
Understood. So you want to add average to this point to go to the
Yeah, because
value.
all previous actual data points were average offsetted from my predictions, right? So I'm just thinking, does it add that actual
See,
average
mathematically,
offset or no?
yeah, no. Mathematically, what you're telling may be making sense because you can add the average error and comes to the nearest one. But that doesn't help in this kind of predictive algorithms. Yeah, maybe I understood what you're telling. Mathematically, it makes sense to add it. But here it will not help. No. Because this is average of only this sample. It's not an average of the population. If you understand the sample data and the population data.
Yeah, I understand. It's the average.
So just average of the sample, right? Now, how your sample is a representative of population, you don't know that. So that way it will not help. Sample size and how good sample is to the population like that. So let's not get into there. But here, this is how we perform the prediction. That's all.
Okay.
Okay, so this is intuitive understanding of how gradient debt rule will help us reaching to the minimum value. Okay. So, okay, now here this is very simple equation. New value of theta, old value of theta minus, this is something which is we already have. We take from a previous iteration. The only two unknowns are here, this and this. The effect of these two unknowns, that's what I'm trying to explain intuitively. The first effect I have already explained. What is the effect? Whichever values of theta 1 we are taking it, this partial derivative will ensure. And this entire equation will ensure that we are reaching to the minimum. Now, the next I will explain what is the effect of this alpha. See, in some book, you may get this as a alpha. Sometimes it is also written with this symbol of eta. So these both are same. They are known as a learning rate. It's a name given as learning rate. And this is something which we do not learn during the training. We assume this value as a constant and then start the training. Anything that we assume as a constant value and start the training are known as the hyperparameters. This is one of the hyperparameter. Likewise, you will see another hyperparameter when I'll talk about regularization. Every algorithm, there are hyperparameters. So a kind of a design choice, when we fix any design choice here, what is the design choice? What value of alpha we should choose? It's a constant, but we can choose any value of alpha. So what value of alpha that we should choose so that our gradient descent works proper way. So that intuition I'm showing you now here. Okay, this is a learning rate. What happens if alpha is too small? So let's see. You have a too small number multiplying by this partial derivative. Tell me mathematically what will be the effect?
Too many iterations.
More iterations.
Okay, no, with this simple maths equation, what will happen? We are doing this new.
Small
This
change.
is old. Very small change. So too small number with a big number, that means what we are doing, a very small change will happen. Over a time, we get many number of iterations. Our training process will become slow. Gradient descent will become slower because we are reaching towards the minimum. Our step size is simply reducing. So theta 1 changes a tiny bit on each step. Hence, this gradient descent will become slow. It will take more time to converge. That's again very important. Here, it's just a linear regression. And we may be talking about just say maybe 10,000 examples or 20,000 examples, say housing price prediction. We can have the data of 10,000 houses or 20,000 houses, but the gradient descent algorithm is used for other machine learning, like neural network also we use gradient descent algorithm. So this convergence is very important. That's a training time. So the time is more, gradient descent is slower. Suppose if we have this is a very large number, what will happen? Theta 1 is changing. So new value will change drastically. It will keep on changing the sign from positive to negative, negative to positive, because it's a large number. So you
The
can
ball
say
will basically bounce off the.
bounce.
It
Yeah.
will never converge.
Then while bouncing, it will may diverge. It may not converge at all, or it may diverge. Sometimes you can say it may diverge. So this is the effect of alpha, and this is a constant. So there are a method known as a hyperparameter tuning. Probably sometime later we will talk about it. In a simple way, you can say it's a kind of a trial and error. You have to come up with the best possible value of alpha so that your gradient descent training, your model training will become faster as much as possible, and it will converge. Our cost should reduce. When I say it is diverging, you can say the cost will keep on increasing,
But
right?
is it possible that it will ever diverge? I mean,
Yeah.
oscillation is possible definitely because the sign of the derivative will also change, right? When it comes from left to right or negative slope to positive slope.
Hmm.
So it will always
Yeah, it
try
is
to
possible.
reach to the minimum, but may oscillate.
It may oscillate. So the good way to find out this, either you can write a Python implementation or simple Excel file. If you do not know so much of Python in detail, take an Excel file, give with this one theta 0, theta 1 example, just fix the theta 0 and tweak this alpha values, different values, and see what is happening. Just take 3-4 examples. Like here we have given some 3-4 examples, right? Mileage and car price or housing price. Small data set and keep on seeing what will happen. For a certain value, it may diverge.
Ma'am, if we can stop the moment it is increasing to previous value, that can also be a error.
Sorry, what?
If in the large number case, if we can stop the algorithm the moment it is increasing to the previous value.
There are various convergence criteria. Correct. Sometimes it might temporarily increase and then again come back. That is also possible. So there are various ways to convergence. There is no fixed thumb rule. There is no fixed formula when to converge. The one is when the very simple one is when the theta stops decreasing. The one is the another simple one is just give random any number. 100 iteration, 200 iteration. That by experience you come to know what kind of a data set, what kind of a problem we are talking about. And then we have very specific convergence criteria. Or this one I said, where error keeps, or the decrease in error stops or error becomes 0. Or yes, if the error is increasing, we can observe it is continuously increasing. That means there's something wrong in the hyperparameter itself. You have to change the hyperparameter value and retrain the model. So this is the alpha. Right now I've introduced one hyperparameter called learning rate. Thetas are the parameters. That's what we learn during the model training. During the model training, we keep the fixed values of those hyperparameters. In this example, it is a learning rate. It's a constant during the training. But which constant that we need to choose, that's not fixed. So there are various, some fixed values, 0.01, 0.1 or 0.5, 0.2. People can start with observe and then change the values of this hyperparameter. And that's very important during the training. The different choices of hyperparameters will give you different results, different performance. So not just model parameter learning, but hyperparameter values are also important. And it is nothing, you're not doing any code, you're simply writing a code in that, say, one time you change to 0.1, other time change to 0.01. It's like a manually, you can write a code which will pick up a different hyperparameter values. There are algorithm in detail, greed search. From the hyperparameter values, you have to automatically search the different values. But for a simplicity, you can understand that manually you're changing different values. Like in a code, you change first time one value, second time second value, and so on. So that it's kind of a trial and error, which one will give you the best results. Okay, so how will this say this is another graph so that we understand the effect of hyperparameter alpha. So again, this eta is a learning rate. So as I said, some book is writing as eta and some book uses a symbol alpha, but both are same learning rate. Okay, this is some example x1 and y. So some regression example with one feature. And here we have the eta of 0.02, 0.1 and 0.5. 0.5 is too high value for some data set. As you can see, it started from the red line that you see at the bottom. Started with this line and then overshooted and going in the other direction. For 0.02, when we started the red line, we are not reaching to the minima value. And for this appropriate value of eta, we started with some red line, and every iteration, we are able to reach to the best possible line, which can approximate our data points. So this learning in it is also very important, whether we will diverge, will converge, and how many iterations we will converge. Okay, so that's for now. You can ask any question on this gradient descent. Then I'll go ahead. Anywhere.
Yeah. Why we
Hmm.
call it descent? I think you answered that, but just
Descent. So it is, we are descending here, correct? And
Okay.
this is a minus sign suggests descending. Some book you will find it is plus. Then it is ascending. In that case, it is talking about a concave function. But here in this case, we are using a descent and we use this minus sign. Yet
Oh,
the cost function we are reducing. Okay, so then I'll go ahead. Now in the second session, I had explained what is the feature scaling. Does somebody remember feature scaling?
yeah.
Using exponential x square, x cube.
Bringing
No, no,
the
no, no, no.
values, bringing the values in
The max
specific
of the
maybe
value and
minus
into
1 to
y.
1.
Yes, bring the value in the same scale. Say I have a data set, same housing price prediction, number of bedrooms, maybe 2, maybe 1, maybe 0, maybe 3, maybe 4, maybe 5, or maybe up to 10 bedroom. And then I have size in square feet. This is another feature. So it could be 500, it could be 1,000, and so on, up to say 10,000. So these two features are of different scale, and we use a min max normalization or a standard or standardization, that is z-score standardization. These are the two popular normalization techniques that we use, and then we try to bring both the features in the same scale. Why? There are many places this is what is required. So feature scaling is one of the pre-processing technique. We will see direct effect here in the gradient descent algorithm. Now, this feature, so this is x1, theta 1 is a coefficient of x1, and theta 2 is a coefficient of x2. This is x1, this is x2. And if we do not do this feature scaling, and we try to use those values as it is, and then calculate the hypothesis function, then calculate the cost, and then take this plot of the error surface. So this is a cost function plot for these two different features, theta 1 and theta 2. You see, this is elongated ellipsis that we will get. And then we run the gradient descent algorithm. We randomly start anywhere. And then each step, the path that goes towards the minimum is a longer path. That means
Madam,
without
can I ask
feature.
one? Madam, can I ask one
Let me
question before we
complete one
speak
thing.
on this feature scaling? Yeah.
One
okay,
minute,
okay.
1 minute. Let me complete. I've already started, right? Let me complete this. Yeah. So what we are doing, we have started with this here, and then we are going towards the minimum. And you can clearly see, this is all experimented and done. Graphs are created. And we can see the path is longer versus when we have both the features on the same scale. We have performed feature scaling, both the features on the same scale. Then we learn the parameter values of theta 1 and theta 2. We try to plot this j of theta error surface graph. And we can see from wherever we are starting is a straight path. Path is shorter compared to the righter one. That means in terms of a convergence, this is faster. I can say this is with feature scaling. And this is lower without feature scaling. This is the effect of feature scaling on gradient descent algorithm. Yes, you were asking something.
Yes, madam. Madam, the question is more towards how do we practice this gradient? Because when I try to program this in after the last class, I was just trying to play around in Python. It just gives us an algorithm, and then so the only way is to, or what is your way of recommending? How do you recommend for us to practice this, madam? see, we understand the concept of how gradient descent works. And if I have to practice with more like with some data sets and all, how do you recommend for us for further exploring and learning doing a deep dive on this?
See, for one way is you write the code in the Python from a scratch where you have to write all this equation, gradient descent algorithm in a scratch. Other ways is use the sklearn library where you don't need to write any gradient descent algorithm.
That is what I was looking at. So all pre-programmed libraries are available. So
Yes.
we have to understand this a bit deeper. So how do you recommend that?
So you have to write a code from the Python from a scratch. The same data set that we use it from same data set, rather than using those sklearn library, use the mathematical equation, use the hypothesis equation. You should know how to write the hypothesis h of theta, theta I into xi.
Yes.
Take in a pandas data frame, take the W's, initialize it in the some array, so that you have to learn how to do that.
Okay.
Madam, I have a point, madam. Even
Yeah.
that the Python, the sklearn will never give the alpha, right? We have to give the alpha to the algorithm. That's where learning will come.
Learning rate, yes. You have there is some default value. If you see sklearn library, there may be some default value, but yeah, you can give the learning rate, right?
Change and we can learn what it is.
That's what is manually have to keep it. Yes. It's simple. One alpha equal to, it's not a difficult thing. When it's in the bracket, you call this, I'll show you probably next class, this one demonstration. But in webinar also, you will have linear regression first webinar. No, first webinar is on data pre-processing. Or I'll show you. So there you can change sklearn. It's very simple. Code is very simple here. 4-5 lines of code using sklearn. Yeah. So now I'll go ahead. And we will solve this further, and I'll formalize this equation. What is the final equation of gradient descent so that you can actually write the code? Okay, so this is our cost function of linear regression, mean square error, and this is the weight update rule. So what do we need here? We need to find out this partial derivative. So right now let's concentrate mathematically. How can we find this partial derivative of this cost function? Partial derivative with respect to thetas. How many thetas? How many features you have? Those many thetas we need to find the partial derivatives. This is the equation 1 upon 2n summation h of theta x and y. And what you see superscript is I. That means number of, it's a training example. Its partial derivative we need to find. For a simplicity, let's say find out a derivative of the cost function with respect to just one training example. So when I say one training example, I'm getting rid of this n, and I'm also getting rid of this summation, and I'm also getting rid of this superscript I. So our equation becomes very simple. This is the hypothesis function for one training example. Half, this is prediction h of theta x minus y the whole square. Again, you have to use a derivative formula, partial derivative formula. So find out what are the formulas. So based on that formula, this is what is being solved. So it is 2h of theta minus y, 2 gets cancelled. This 2 gets cancelled for, it's called a mathematical convenience. This 1/2 has been added in the MSE. Okay, so now when we solve for this, again, because I cannot tell you anything more, you don't know, you don't remember the calculus formula. But the first term we got h of theta x minus y. Now the second term partial derivative is this term. Okay, simply let me write this. Theta j. So let's do it for a theta 0. And what this equation will become? Theta, what is this equation? Theta 0 x0 plus theta 1 x1 up to theta n xn minus y. So I've simple expanded this equation and say I'm finding out the value for theta 0. Now, what will be this equation will be reduced to? Anyone who remembers the
0
zero?
minus.
No.
Because
See,
there's no theta in the derivative, right? It's constant will become 0, right?
no, we have a theta 0 here. 1. No. Go back and refresh your calculus. Okay. This all are constant. Because we are finding with respect to theta 0, rest all variables will become constant. So that will become 0. But what will happen to this theta 0 and x0? So in that x0 is a constant, that will come out. So this will x0, theta 0, derivative of theta 0 with respect to theta 0. So that will become 1. So answer is x0. For theta 0, it is x0. If we have a theta j, then this equation will be reduced to xj. Whichever theta, theta 0, theta 1, theta 2, theta and so on. So that xj term, you can see such a complicated looking partial derivative is reduced to xj. This is derivative of j of theta with respect to theta j is nothing but y hat, that is prediction minus actual multiplied by the corresponding feature value. This is the equation. When you need to code it, you can use this equation directly. You don't need to write the equation for the partial derivative. So why are we doing this this derivation? So that we can simplify. So now if I write this in the form of the equation. Okay, before I'll show you in the form of this equation, what we need to do. Now I need to add all the training examples, because what I did in the previous, this we are getting just for one training example. So when I add all the training example, I'll have this n added and this summation sign added and this superscript added. Rest of the things will not change. So here this 1 of n will be added. Summation sign will be added and you can clearly see this is getting added. And for all the features, we are writing this a generalized equation, not only just for one feature. So this is a generalized equation here 0 to d. D is the dimension of the data set and n equal to the training example. So if you understand how the first one training example equation has come, you can understand how this n training example and then all features has come. But we can simply write this is theta j, new theta is old theta minus alpha, and this derivation is reduced to this equation. And these are the equation that you need to code it in the Python. So what we do, repeat until convergence. You can define some convergence criteria. Rather than writing alpha into partial derivative of j of theta, what do? We can write theta 0 equation separately, say theta 1 equation separately. Here just example, theta 0 minus alpha 1 by m. Say m is a training example. Some one variable training example. H of theta minus y. Why we are doing theta 0 separately? Because what is the x0 value? X0 is a dummy variable. It's not a feature. It is always 1. So we do not have this x of x term over here multiplied by the corresponding feature value. And for theta 1, then we write this equation. It's such a simplified equation. It's 1 by m is your, because we are taking for all training example, summing for all the training example, hypothesis function minus actual value multiplied by corresponding feature. Now here we are talking about theta 1. So the corresponding feature is x1. And important, when you implement in a Python, we have to update this simultaneously. That's why it is known as a simultaneous update. So once we calculate theta 0, we store it in temporary variable 0. Then we calculate for new values of theta 1. We store it in some temporary variable. Once we do it for all the thetas, if you have 50 features, you will have 50 thetas and 51 thetas, and then you will calculate for 51 thetas, 51 temporary variables, and then update the existing thetas simultaneously. Can somebody tell me what is the reason? Simultaneous update, again, very important from the implementation point of view. Any guesses why? Am I audible?
Lesser number of iterations?
No.
So that loss functions remains minimum, loss function value?
It is to maintain the integrity of the system because they are simultaneous equations. So it's a linear system of equations where you have to maintain these variables simultaneously.
No, it's not simultaneous linear equation.
Because it's a
See,
slope, right? Mx plus c, m and c you have calculated.
this hypothesis function, we calculate once with the all same set of parameters. It is the same. Hypothesis function will remain same for the same theta 0, same theta 1. Now, suppose if we do like this, something which is incorrect implementation, theta 0 would be the new value and theta 1 would be the old value in this partial derivative calculation, which actually got this hypothesis function in it. So when we calculate hypothesis function for one iteration, we use the same theta 0 and same theta 1. I mean to say, if it is new, then both should be new. If it is old, both should be old. So if we do perform this kind of update, in theta 1 calculation of h of theta over here, we'll get theta 0 new value and theta 1 will be old value. So that is the reason that we perform simultaneous update. And then after this is the first iteration. This is one iteration. Calculate all the update all the theta at the end of the iteration, like this. This is one implementation tip. And now, okay, so it's a simple gradient descent. It's two-step. Initialize this theta with any values. Apply this gradient update rule. Now you see there is no partial derivative over here because we have derived, we have solved that partial derivative, and it is simple. We have come up with this simple looking equation. This is actually very simple. This is prediction minus actual multiplied by corresponding feature value. We'll solve a numerical, so it will be more clear. Again, with pen and paper or with Excel, you can do it. And now, convergence criteria. This is one of the convergence criteria. If the change which is observed from the new and the old theta value, take a L2 norm of that. If it is less than some epsilon is some very small value. If the change, in other words, if the change that we observe in the theta values in every iteration is very, very small, then we can stop those many. I mean, we can have that as a convergence criteria. We can stop running the gradient descent iterations. And this is the, if you, again, it's a vector concept, how to calculate L2 norm. V is a vector, and then this is the formula for the L2 norm. Here, this becomes the vector. Okay, so clear with the batch, clear with the gradient descent, then I'll go ahead with the batch gradient descent.
I have a question here. Now, this particular point says that if theta new minus theta old is less than some epsilon, then we must basically assume that there is a convergence. Now, for example, I start off with a very small alpha learning rate, right? Then there's a good chance that my theta new minus theta old is still going to be lesser than this epsilon. But then
No,
reality
Mani. We use a very small number for this alpha. Very small number. Not alpha, sorry. This epsilon. Yeah, very small number.
Okay. So you're saying that there is no probability of that happening.
We cannot control that if that is happening.
Okay. Thank you.
Even if it is happening, you cannot control it. You have to change the value of alpha.
Got it.
Okay, so now
Ma'am, here theta j is some random slope or
what?
Theta j.
Hey, this is a general equation. Okay, J runs from 1 to D. You have D features, then it is running from 1 to D. Okay, let me see. 0 to D. We are taking x0 also into it. 0 to D. What is this J then? What is this theta then? I've shown you in the previous slide. Here in this case, J is 0 and 1. Theta 0 and theta 1. So when I say theta 0 and theta 1, how many features you will have in your data set?
2 features.
2 feature or 1 feature?
2 features. 0.
No. Anybody? How many features you will have in data set?
One feature. Theta 0 is constant. Theta 1 is x1.
Yes. Theta 0 is a bias term. This is the bias term. It's a constant term. This is what I started first class. What is the, when we started with the linear regression concept, first class, bias term, it's a B term. Only the symbol is changed. Variable name is changed to theta 0. Okay, we have just one feature. So theta j is a generalized way of writing mathematical equation. Theta 0, theta 1, theta 2, up to how many features you have. For every feature, you will have this coefficients, weight coefficients. They are nothing but the parameters of the model. So this is a general way of writing the equation where I, superscript I, denotes the example number, subscript j denotes the coefficient number in this case. If it is xj, for every xj, you have a corresponding coefficient theta j. You have to also get used to of how to write a mathematical general equations.
Okay, and in this gradient descent algorithm, why did we take the derivative with respect to theta j?
Why are we taking that derivative? That is what you're asking?
No, why did we take the derivative with respect to theta j only?
I actually have explained that. Can somebody else answer her question? Yes. Why are we taking this derivative? It's intuitive understanding. That's how it started.
To get to the local minima.
Derivative to reach the minimum point. That point I have understood, but why only with respect to theta j?
Okay, what is a cost function equation? That also I have explained. Where is the cost function equation? Yeah, this is the cost function equation, right?
Yes.
What can we change in this equation? That we have a control over. We can change and we can reduce the function value. We can change the function values. Forget it, minimum, maximum. But what is the variable that we can control in this?
Only the slope represented by theta.
Now talk in terms of mathematics. So we can only change is what is theta. X is given to us, Y is given to us, N is a constant number of training example. So we can only control theta. That's why we are taking this partial derivative only with respect to theta.
Why it is denoted as theta j instead of theta I? It is same as feature, right?
It goes for theta 0 to up to theta j. J is nothing but number of parameters. Sorry.
I just explained. Yeah. I just explained that also. This is the way we write mathematics. You have to understand how to read the mathematical equations. Even that also I explained the superscript and subscript concept in the beginning. Did I explain that when I started with linear regression? What is this xj? You tell me, what is this xj? How do you read this xj? X and then subscript j.
X at instant of j.
Jth term of jth independent variable.
Jth feature.
Jth feature, jth independent variable, right? If I have a coefficient with respect to this xj, I write theta j. So what is this theta j?
Wait. Wait for the x.
Wait for that x. That's why we write theta j. I think you're asking me the same question again and again. I just explained what is theta j. It's the same thing. This is the way we write it. So when we say j equal to 0, so how will I write this? Sorry, if we go ahead with this space, I think we cannot go ahead with, it's a very huge syllabus. Please go through the recording again and again. Get yourself your maths fundamentals. I understand maybe you have forgotten everything, but simple understanding of maths is very, very important. How do we write this maths? I understand your MFML is going a little in a different pace, but you can take your own effort and understand how the equations are written, how the equations are read. Here I'm explaining to you how to read the equation. So this is theta j. Suppose if I write, okay, xj and theta j. If I say j is equal to 0 to d, so I have, this is summation. J is equal to 0 to d, x0, theta 0, plus x. This is a summation sign. So x1, theta 1, x2, theta 2, x3, theta 3. Now suppose if I want to write a gradient descent equation for individual parameters, we write. we change individual parameters. So it is, say this is new, this is old, and we have this is what is theta 0 minus alpha, partial derivative of g of theta with respect to partial derivative with respect to theta 0. That means we have come with the new value of theta 0. Similarly, we have a new value of theta 1. So I will write down something like this here. Old value of theta 1 minus alpha, the partial derivative of cost function with respect to theta 1. Likewise, I have up to d. D features, right? J is from 0 to d. So I write d. This is new. Theta d new minus alpha. I'll write something like this. Now, mathematically, I can combine all this equation when I write it. So that's why it is coming out to be theta j new, theta j old minus alpha, partial derivative of this cost function with respect to theta j, where j runs from 0 to d. This is a mathematical way of writing. I hope it is clear now. Yes.
Yes, ma'am. But my question was not related to the mathematical expression. I was asking about theta j also represents the feature. So why are we not considering theta I, but why we introduced a new variable theta j?
First of all, theta j doesn't represent the feature. Theta j is a coefficient of the feature. That is the first thing. And what is theta I and theta j? You said why not theta I, why not theta j? Is it so? What did you
Yes.
ask?
Yes,
I mean,
yes.
these are just a variable, whether you write or I or j. Just
Yes,
a variable.
both vary from 0 to d, right?
Yes, yes.
Even x1 to xn, that also varies from 0 to d, right?
Yes.
Yeah, so
Either you write this way or either you write this way. Just a variable.
yes. So during the summation, it is having two variables. So that is why I asked why.
Where is the
we-
summation?
After the
Where?
after the derivation, we got the final formula, right?
Which slide number? Still, I have to go back.
You can go forward, I think. After
Acha,
complete
that derivation.
Yeah. Yeah. Yeah, here. So here we have written I ranges from 1 to n, and again j is ranging from 0 to d. So even the j varies in the same way, right?
I is for training example. I is 1 to n. J is for feature. For corresponding value of theta 0. Here it is theta j. It is a xj. So there's a similarity. This is what you are asking, right? Theta j. If it is theta 0, it will become x0. If it is theta 1, then it will become here x1 at this point.
Okay. Okay, got that. Thank you.
Okay, now there are variants of gradient descent, very simple change. Batch gradient descent. When we take all the training examples together, so if you see in this, there is a summation sign. That's what we also used, the summation sign in the previous slide. There is a summation sign, M. Sometimes it is M, sometimes it is N. They are just the variables. So when we take all the training examples, then it becomes the batch gradient descent. Now just imagine you have so many training examples, 10,000, 50,000. Then one iteration of gradient descent becomes very slower. In that case, we have the variation to this. The other variation is just take one training example, calculate update all the weights, and then for the next iteration, use the next training example. So that every iteration becomes faster. In every iteration, there is no summation sign here. If you see alpha multiplied by simple hypothesis for that training example minus y, y hat minus y. So here in this case, there is no involvement of all the training example in every iteration. One iteration, one training example, another iteration, other training example. That is known as a stochastic gradient descent. But we definitely update all the parameters for only involving only one training example. And in between this two, we have something called mini batch, which is more popular, where we divide our data sets. We divide our data set into n batches, mini batches. Like say, if I have 10,000 data points, I can create a mini batches of 1,000 or mini batches of 500. Generally, we do it with any number which is power of 2. So those number of mini batches are created. In each iteration, we only take those training example in calculation in this summation sign. The summation indicates that we are calculating this difference for every training example, and then we are summing them together. And so that is batch. Mini batch, we reduce, create a batch, and dedicate one batch for one training, for one training iteration. That's mini batch. So why this different one? Again, it is explained with the help of this graph. Say this is a stochastic gradient descent, where each gradient descent iteration, we just use one training example. Then we see this path is very going in a zigzag manner. Sometimes it may not reach to the convergence point. So on the right hand side graph, there is example of 3 such technique. The blue one is a batch gradient descent, where we take all examples together in every gradient descent algorithm. So the trajectory is very smooth and it will reach to the end, but it is slower. Then the green one, first the red one. It is a stochastic, where you can see many zigzag patterns you are seeing. It may revolve around the minimum, but it may not reach to a minimum point. Compared to the mini batch, it's a green trajectory, which we can still reach to the minimum, but again going in a very zigzag manner, but faster. So these are the pros and cons of these 3 methods. And most popular one is mini batch, because it will reduce the time for each gradient descent iteration. Where in batch 1, it will increase the time for gradient descent. So if you have a smaller data set, you can always go ahead with the batch gradient descent. But when you have a bigger data batch, it is always good to define the batch size, smaller batch size, so that every iteration will become faster. So this is more of the practical performance point of view, but the equations and all will remain same. The concept, the algorithm will remain same.
But ma'am, in case of batch mode, what if you have multiple local minima, and how will you find out? Let's say each batch will give one kind of minima, and
Will we 1 minute?
Yeah.
Will we have any local or global minima in this case?
Will there
The
be
question is
no. The question is there will be multiple local minima, and out of
no.
that ones can be.
That's what I'm telling you.
Convex form.
Sorry, what is that?
See, when we say a batch, see, first of all, we are using a gradient. Our cost function will not change. Only the training examples are changing. In every iteration, we will get some minimum, but it will be a global minimum. But when I say every iteration, we are also updating the parameter values. So you're trying to say that something like this, what we will get?
Yeah, so something like
No, we will not get. We'll not get something like this. Your error surface will remain same.
But in the previous slide, you mentioned that we will. Can you please go back to this one? Yeah. So divide the training instances into n batches of size m each, right? So in each one of the batches of n, let's say we get one minimum, right? We need to have one step where we need to compare the minimum of all the batches to find out what is the global, right?
No. See, what is happening here? We use that same batch, and then what are we doing here? We are updating the parameters. We are already updating the parameters.
But that is only within that one batch, right?
But then you are going ahead with the next batch. In the next iteration, again you will update the parameter.
Oh.
So I say that with whatever we get first batch, that theta 0, theta 1, theta 2 will be applied to the second batch, and if updation is required, it will update.
Yes. Yes.
Oh.
So the first, initially we start with any random value. Those random values are only going in the first iteration. Whether you take batch, mini batch, or stock, just one example. In the first iteration, when we are updating, when we are calculating, these are the new theta values will go as the initial values for the second iteration.
Okay. So in that case, how is it really saving on the computational resources? See, anyway, n times m is anyway happening, right? In terms of the processes, m times n is anyway happening. So why batches? Why not just go through the entire list one?
Yeah. So first of all, every iteration will become faster. It may happen that with a certain training examples, we are able to reach the minimum value. Not all training examples are contributing to the cost function. So that way, every iteration is becoming faster.
No, but
and then
unless you go through all the training, all the data in the training set, you won't know what is the global minima, right?
Every training, see, first of all, there's no concept of global and local minima over here. Okay.
Yeah.
Here, when we say this surface of say theta 0 versus j of theta, here only we talk about global minima and maxima. How are we getting this plot? When we are getting this plot with respect to theta 0, say theta 0 or theta 1, whatever, say let's say theta 1. Now here, we are calculating this weight update from the previous one and the next one, old and the new. In weight update, we are taking all the training, or maybe the mini batch of training examples, and then we are coming up with the one value. So the error surface will not change. The shape of the error surface will not change. Whether you take 10 examples and calculate and update the theta 1, or you take 100 examples. We are interested into the shape that, so that we can get rid of the concept of global and local. Whichever minima it will reach, it will be global minima. Here in theta 1 update, it won't change. Shape won't change.
True, but somewhere in this logic, there should be a break statement, right? Without which we are anyway going through n times m.
We are going to n times m's. We are just simply reducing the each iteration time. So after iteration, we are able to see the weight update. When I take entire batch, say 10,000, I can see weight update only after I go through the 10,000. Now think of a situation where other way of looking at it, you see it is a weight update is happening in some reverse direction. So you may have a wrong value of alpha you might have given.
Exactly. So where are we doing the check in this algorithm? We are not checking.
This is just we are not checking. This is a manual you can check. See, hyperparameter values are not checked in the code. This is simple a gradient descent algorithm which assumes alphas are constant.
Got it. Got it.
You have to write down in the code to check on that.
Okay.
Manually or just write one script which will check on that.
That's what I was going towards. So thanks, ma'am.
Okay, now just see this one question and try to solve with pen and paper. Then only you will understand the entire process. A lot of doubts will be clear. Will you try to do on your own? Can I go ahead and I discuss about this in the next class? I want you to solve this problem. Entire problem is solved.
I don't think we have these slides. I was looking for these slides, but it wasn't there.
Okay, this I'll update. Today I'll do it. So just take your time, read this with pen and paper, and I'll discuss this question in the next class. So first try to grasp the gradient descent algorithm and then solve this end-to-end numerical. So what we are asking in this question, some sample data set is given, read it, what are x1, what are x2, then what are theta 1, theta 2, and then the few steps are already shown over here, some calculation is shown over here, final values are shown over here. So take your time, first understand gradient descent and try to solve this, and then I'll discuss this problem in the next class. So is that fine? So today I'll start with I'll continue with the new concept. Yes? Please mute yourself. Mute yourself. You're talking.
Ma'am, just a small question. In case of large data sets, right? You said that stochastic or mini batch is preferred. So is there any, for these cases, mini batch is preferred, and For this case, stochastic is preferred. Is there anything as such?
No. Stochastic is generally like just one training example, right? So it will again, iteration will be faster, but you may not get the final answer. It may not converge to a minimum point. So mini batch is more common. The batch size again is a hyperparameter. What should be the mini batch size?
So that's why it's preferred or popular.
Mini batch you are talking about, right?
Yes.
See, you give mini batch equal to all training example or give a one training example or come up with any mini batch size. So that's a hyperparameter.
Yeah.
So ma'am, the batch size, the number of training examples that we have, with that we are determining that. Let's say you have 10,000 records versus million records. Will the batch size dictate that? Like, how does it work?
Yeah, batch size is that. So out of 1 million, you want to create a batch size of say 1,000 or say 10,000. 1 million is a big number. So you want to create a 10,000 batch size for every iteration or a 1,000. And then like all this, you can write in Python or it is done in sklearn. It's like one hyperparameter where you can define the batch size, like how you can define the alpha, you can define the batch size. Randomly. Now again, this is a thing. It's not like, all the training examples are equally divided. Like first 10, say, for example, 1,000 example will go in first batch, second 1,000 example will go in second batch. No. It is sampling with replacement. That means from the, you can have a ball of say 10,000, randomly 1,000 balls will be picked up, given to one iteration. Then for a second iteration, those 1,000 balls is going back in the bag. Shuffle the bag, pick up another 1,000 example and then giving it to the iteration. This is how the iteration happens. So we get a lot of varieties in the, a lot of different representation we can get in every iteration. So that's another way, another advantage of mini batches. It's not like first 10,000, next 10,000 and so on. No.
What is the advantage of doing that with replacement, the sampling with replacement?
Say, suppose your data set has got such a way you have first 10 example, say first 1,000, it's a cat and dog, very simple example, cat and dog classification. First 10,000, first 1,000 cat, second 1,000 cat, third 1,000 cat, fourth 1,000 dog, another 1,000 cat. So you're understanding, we need to have the good representation in every iteration. So sampling with replacement is a very common strategy for all such kind of task.
But what if you draw that 1,000 out of, let's say, 10,000 randomly? Anyway, the randomness is guaranteed, right?
So that's why it's random. But then the previous 1,000 we are removing, right? Randomness is guaranteed.
It's a random set. So what's the problem?
Okay. You're talking about why. No, in the practical strategy says that take this randomness from all the included, all the previously taken and put it. So multiple training example can come in multiple iterations. So that also randomness we want to introduce over here. Not like once it is done, it is done. Like once one training example has seen one iteration, it is done. No, we want to create a randomness in that also. That's why it's going in the replacement.
But the downside of that is some training set may never get run through the gradient descent, right?
Yeah, but the advantage is that other training example will get a chance to go through iterations many times. So we are approximating mini batch to a batch performance. Where batch, what happens in case of batch performance? Every training example goes through many iterations. But we want to increase the iteration speed. So we are coming up with this mini batch. So the more, see, again, you are weighing down and weighing up which one is more important. Okay, we want to approximate mini batch to the batch performance. So let's have more, many training examples, see many iterations. That's the advantage. We are putting more effort, more emphasis on that.
Got it. Okay. I think this is more of which domain we are working in and like what is the results of the previous and stuff.
And you also have to see how our libraries have implemented this. I think sklearn has implemented in random sampling with replacement. Yeah.
But can you choose in sklearn, can you choose whether you want it with replacement or without replacement?
No. That only batch size you can choose.
Okay. Got it.
Okay.
Thanks.
So solve this gradient descent and next time, if you do not understand, I'll discuss it. Now, what is remaining is learning model parameters. So gradient descent is also one of the way of learning model parameters, which is an iterative solution. For a linear regression, we also have an analytical solution, a closed form solution. The life may become a little simpler if you have a smaller data set. No need to go for this iterative solution. That is what is I'll talk about, then linear basis function model, quality of fit, and evaluation metrics. So these are the remaining for this module. Okay, so in this for concept of closed form solution, again you have to understand the concept of vectorization. When we do this vectorization, we are able to create more compact equation, and we are not using the for loop. The for loop, like if we do not use the concept of vector and a matrix multiplication, when we code it, you have to write so many for loops. And for loops are slower than the matrix multiplication. So that is what is more of implementation advantage when we do this vectorization. Our libraries like NumPy, they are supporting this matrix multiplication, and this ML and deep learning models, we can put it on the something called graphical processing unit, GPUs, which also take advantage of parallel computation. So for the time being, you can understand only that much. If you do not understand in detail, it's fine. In deep learning, you will see again this vectorization effect. But this linear regression closed form solution, we can have using this concept of vectors. This is the hypothesis function. I will write down this hypothesis function in the form of the vectors. This summation, suppose if I just want to retain the function as it is, how will you code this summation? How will you write in the code? Yes.
For loop.
There will be a for loop. Yes, there will be a loop. So for loop is a slower. That's what I said. Instead of that, I can define theta and x as a vector. So we have theta 0 to theta d. Similarly, we have x vector. Say example of just one feature for the simplicity. But yeah, here it's given example of one feature, but you can have x0 up to xd. And then we write something called a dot product, vector dot product, theta transpose x. Okay, this is a x, which is nothing but a dot product between theta and x. So there is a formula. This is a formula actually for the dot product, theta transpose x. So then our hypothesis function will become theta transpose x in the vector format. Say in this example, I have just one feature. So what is the x? X is a column vector and x transpose is simple row vector, just a way of representing row and the column vector. So here we have number of years of experience as the feature, just one feature example here. So it is what is x1 and this is x0. X0 is always constant 1. So x0 has got a coefficient theta 0, x1 has got a coefficient theta 1. And then you can actually perform this vector multiplication, dot product multiplication, and we can directly get the hypothesis function. That is for one training example. Suppose we have many training examples. We stack all the training examples vertically together to create the matrix. So this X capital matrix is created where the number of rows are nothing but, number of rows are nothing but, you have the training examples and we are stacking all the features together. So number of columns are nothing but your features. This way we create the X matrix where rows are training examples and columns are features. So each training example in one row. Each row is nothing but one training example. So I want to write a very simple equation, just one equation. So when you write a NumPy code, it will become very simple. Our hypothesis function is capital X, which is a matrix that we just defined, multiplied by theta. Theta will remain same for all the training examples. It doesn't change. So theta is a vector, and we also will create a y vector, the actual y vector, where we have the actual values of each of the training examples. So this is also a vectorization. Here, like in this example, which is given, theta just 2 theta, theta 0, theta 1. X is what? These are the 5 training example, 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And here I have what? This is for x0 and this is x1, x1. And this is just y1, y1 feature.
X0 is taken as 1.
It's always 1. No, it's always 1. Just for a simplicity, it is mentioned.
Okay.
Okay, just a minute. I'll just take a 2 minutes break. I'm getting an important call, just 2 minutes. Okay, what I was explaining, 1 minute. So this is your training data set. 5 example, you can see 5 rows, and we have just one feature, x0 and x1, and corresponding y value. So that also we have created a vector. Okay, so that vectorization is important. Now we will convert our cost function in the form of the vectors. This is a cost function, 1/2n summation of I is 1 to n, h of theta, x of n. Now you should know this is I, superscript, is the training example. Okay, first what we will do, we will create a function for one training example. We are summing all of thetas together. So I can write h of theta x equal to theta transpose x. And still I have all the training examples. So superscript I is still here and summation sign is still here. Then we'll get rid of this summation where we will create a matrix for x. So now the equation will become, if I write down here, 1/2n, 1 minute.
இன்னைக்கு உங்களுக்கு ஸ்டிக்
You're asking.
வாக்கிங் ஸ்டிக் ஆர்டர் பண்ணோம்ல நேத்திக்கு, இன்னைக்கு வர்றதுக்கு வாய்ப்பு இருக்கு. வந்ததுன்னா நான் சொல்றேன், வரும்போது கீழே போய் வாங்கிக்கோ.
Right, Swami.
So this is 1/2n. Then we have here x theta minus y the whole square. So we convert into vectorized form. Now there is more mathematics. It is not just for your understanding, not important from the exam point of view, how we are coming up with the final equation. We can find out this theta, but there is a long derivation. So if you are interested, should I explain this?
Yes, ma'am.
Yes, yes, ma'am.
Yes.
Okay. So again, it's your vector basics. You may not remember, but again, you have to go back and verify how it is coming up. So here I have modified my cost function with respect to this vectors and the matrix. I have something, if we have the matrix or the vector square, it's nothing but x transpose x. So here I have x theta minus y is a vector whole square. So it is x theta minus y transpose x theta minus y. This is what I will get. Now I'm simplifying. I'll simplify further. How we can solve anything analytically. It's the function optimization problem. If we want to find the minimum value of any function, we take a derivative of that function with respect to the variable equate it to 0. Very simple solution. So here we need to find the minimum value of cost function. We take the derivative of cost function with respect to theta, because theta is the only one that we can control. And we take this partial derivative, equate it to 0. So I've taken this simplified form in the form of metrics and vectors, g of theta. We'll do further simplification, and then I'll take the partial derivative. So see, first we are multiplying this 2 brackets, simple multiplication we have done. So this is what? X theta transpose into x theta. So one step is missed. Can say, I'll write down one more step over here, how we are getting this step. I'll write down here, x theta transpose into x theta. So this first element and first element we are multiplied together. Now again there is some formula. So when we have, say, x theta transpose, which is equal to theta transpose into x transpose. So this is what is mentioned here, theta transpose x transpose into x theta. Then we have the second term, y transpose, because transpose is here, multiplied by x theta. Keeping it as it is. Now take this minus y. So minus sign is outside. Y into x theta transpose. So this is what is x theta transpose into y, which is solved to reduced to theta transpose x transpose into y. And finally, we have this y transpose multiplied by y. So likewise, I'm simply multiplying these 2 brackets, opening up 2 brackets, and I got the second line. Now third line, we are doing a simplification, further simplification. How? So say now let's concentrate on this term here. Y transpose x theta. These all are, I can say, vector and the linear algebra using vector and matrices. Some rules are there. In this case, what we can do, I can also write this as x theta the whole transpose into y. These both are equivalent. And then I'll expand this. So it becomes theta transpose x transpose into y. So this second term is essentially theta transpose x transpose into y. And then this minus. So both the terms are same. We are adding them together. So that becomes minus 2 theta transpose x transpose y. The first term I have written as it is. Second and third term I have combined. And the fourth term now becomes the third term. So this is further simplified using the rules. Now we take a partial derivative of this equation and equate it to 0. Let's remove 1 by 2n for the time being. We don't need that 1 by 2n. It's just an averaging function it is doing. So when we take a partial derivative, it acts as a constant. Okay, so when we take a partial derivative of this term with respect to theta, the last term will become 0 because it is a constant. Again, it is with respect to theta vector. So this is a constant term. Now, first 2 term has got a theta. So let's say first term, how will you solve? For the first 2 term, what is the constant? First term. When we take a partial derivative of this becomes a constant, so we can take it out. X transpose x. And then we have derivative of theta transpose theta upon a derivative with respect to derivative of theta. What is theta transpose theta?
Theta square.
Theta square. So ultimately it is reduced to 2 theta. Derivative rule 2 theta, 2 x transpose x, which we have already taken out and multiplied by theta. Now derivative of the second term. Again, what is the constant over here? 2 is a constant. X transpose y is a constant that will come out. And derivative of theta transpose theta is 1. So it has been reduced to this term. 2 anyway will get cancelled. So finally, when we will simply rearrange, we'll get theta value. Theta is a vector. That value equal to x transpose x inverse So X is a matrix with, so there's a matrix inverse multiplied by X transpose multiplied by Y. So if we use this equation in NumPy, you can use a matrix multiplication. We can directly get this theta. No need to do any gradient descent iterations. With linear regression, it is possible. So linear regression has got the analytical solution. Now, what are the constraints to use this equation? When it's a matrix multiplication rules, linear algebra rules, the inverse can only exist if the matrix is not singular. So those rules will apply if the matrix this becomes the singular matrix. That means it's a determinant becomes 0. Then there are certain we have to find a solution, reduce the number of features, or remove the redundant features, or use a pseudo inverse. Those some solutions we have to use it. So there are ways to find out whether this is a singular matrix or non-singular matrix. That is only constraint. If that constraint is satisfied, if this is not a singular matrix, that means the matrix inverse exists. Then we can calculate, apply this simple formula in one equation, you can calculate the model parameters. But then why do we need a gradient descent? Okay, before that we'll discuss, this is just one example, same. X transpose. So we have taken this as X transpose multiplied by X. This is X. Take a inverse multiplied by X transpose. So we have taken X transpose multiplied by Y by. Generally, we define vectors in the column vector format. So when we take a transpose of that vector, it becomes the row vectors. And then at every step, this is resolved. So this is X transpose X, matrix multiplication. Rest of things are same. Then we are taking inverse. So next one is X transpose X inverse. Rest of the things are same. The next is X transpose X inverse into X transpose multiplied by Y vector. And finally, when we do this final multiplication, which is what? X transpose into X, take a inverse into X transpose into Y. We'll get theta values of like this, vector 1 and 1. This is another way of solving using vectorization. So our closed form solution exists. Without vector also we can calculate by putting each of the values, but still gradient descent is popular. Why? Just imagine the matrix sizes. What is X size? Your number of rows are, what does this number of rows represent?
Sample.
Number of examples. And number of columns, number of features. Imagine you have a data set of 30 features and 10,000 example. What will be the size of that matrix X? 10,000 into 30. You have 1 million examples and you have 100 features, 1 million into 100. Now performing that matrix multiplication is very slow. And obviously, if you have enough memory in the CPU to that. So it becomes very slow, slower than the gradient descent if number of training examples become very large. So for large, if you have a very large data set, then generally gradient descent is preferred. And for the slower data set, you can use this analytical solution. Smaller, but very small data set. Even if you have example of 1,000, you can imagine the size of your matrix will become 1,000 into say 10 features. And then how many matrix computation we have to perform? If you look at the equation. One matrix computation of large matrices, then finding of that large matrice inverse, again computation with such a large matrice and so on. So still that is not is the advisable form.
Ma'am, just for the context, like when we say large and very large data sets, what is the kind of order of magnitude are we talking about?
See, till few years back, 10,000 was good.
10,000 is what? Small data set?
I mean, it was large, considered as large. Now we are getting more and more data set. The definition of large is changing. 10,000 becomes small. And now our hardware capabilities are also increasing. So that's very subjective term, large and small now. So it's ever changing term.
So as of today, what is large? In order of magnitude?
So what? So what resources you have? 10,000 is small. I can consider if it can fit in your CPU. I mean, you can run it 1 million example. Yes, it is large.
Okay, got it. And very large is what can we say? 10 million?
Beyond that. Beyond that.
And then 1 million can be small for GPU. So, I mean, again,
Which GPU you have? Yes. If you have a very good computing resource, 1 million is nothing. If you're talking about just laptop and a Google Colab, even 1 million is very large.
Got it. Got it. Okay. Thank you.
Okay, so we are done, I think, right? Okay, so still I have a lot of things remaining. We'll discuss in the next class. I'll upload both the slides. Go back with that gradient descent problem and you can ask me in the next class. Yeah, now anybody wanted to ask certain things?
just one question I had, ma'am. Nothing related to like logic. So we are kind of understanding the intuition behind these, the expressions and all those equations which you are explaining. From the perspective of assessment, do we need to remember them, or they are primarily for the understanding purpose so that we know, like when we say gradient ascent, what happens underneath, right? So is this for understanding or we need
See,
to
gradient
run
descent
through
is a
all?
very, yeah. Gradient descent is a very simple equation. Those simple equation you have to learn. Hypothesis function you need to remember. Very complex equation will not want you to remember for a mid-semester exam, which is a closed book exam. But gradient descent, linear regression hypothesis, logistic regression hypothesis, you should remember. Yes, they are not that complex, right?
The final evaluated equation or the derivation of those final equations also from the scratch, like you have explained.
Smaller derivation, yes, smaller derivation you try to understand and remember. Right now, I can't say about the question paper. No, you're asking from that point of view.
Yes.
Right now, I can't guarantee that because we have many sections, many instructors, but yeah, those derivations are not needed. But what I have explained, a very small derivation that you can remember. So that way, some small derivative formula you should always remember. But open book exam, you will get access to all the books, only hard copies. Then you should be able to derive. So generally, those derivations, if asked, little tweaking, we don't ask the derivations. It's not needed. But yeah, a little bit tweaking we do, and we ask in open book exam, not in the closed book exam. But again, as I mentioned, there are many instructors, many sections, so the consensus differs. Okay, anybody wanted in the beginning, you missed some classes, you wanted to know, or you went through, you did not understand cost function and something like that?
Yeah, ma'am. I'll go through the recording actually. I think it will take some time for me. So yeah, I'll read the recording.
Okay, fine. Thank you. Anything else?
Yes, I have a question, ma'am. Is it possible to map the our classes to the textbook sections? I tried mapping them, textbook and the reference books. I'm not able to.
It's very difficult. So here I've mentioned, right, this is CS3, chapter 3, and some of the notes of CS 2 to 9.
So are you suggesting that the slides are probably the best source of learning?
Yes, but in detail you should refer to
Ma'am, you are not sharing your screen.
Oh, okay. I'll stop sharing.
Yeah.
Yeah, so here I've tried to mention the maximum. See, machine learning is such that there are two good books, Tom Mischel and Christopher Bishop, but those books are written very old and it has evolved over a time. Very different people have come up with a very different, very simplified and understandable notations. So now the notation that we are referring to the CS 229 of Stanford, Andrew Ng's course. So you can refer those notes, and yeah, for theoretical understanding, I'll stay for this particular content, chapter 3. And I think for the chapter 4 also I have mentioned, I mean, which is not CS4, which is not completely done. Yeah. So this two will remain same and few part from this.
Got it. Okay.
It is difficult because there are so many concepts, different concepts explained at different places, and it's combined together.
Yeah, that's what I realized.
But the same concept, this linear regression will take time, but same gradient descent, you use same evaluation metric, everything, concept is going to be same in the future.
Yeah. Okay.
Yes, Bharati, you said something I will be able to complete. It won't be helpful to us. So I understand it won't be helpful, but I also expect that you come with some kind of a background. See what is happening here. We are trying to teach you this machine learning, which say you are learning a Shakespeare without knowing the alphabets. Now, if I start teaching alphabets, will I be able to complete a Shakespeare literature? That is what I'm asking. I'm not asking that I will not answer your questions.
No, ma'am, actually, I mean, it's not your fault, right? But the problem is, I think there is some kind of management issue, right? So after taking admission, there was like quite enough time. If we were have given like the topics and all, we could have,
Yeah,
prepared.
that's what I've given. Yeah, I've given that feedback and I've asked coordinators at least some maths recording and data science. We have a course IDS, so we have a recordings available. So they will to give to the students.
Yeah, so ma'am,
Yeah.
our situation is like 5 days completely busy, right? So in just 2 days, almost 6 hours classes, Saturday, Sunday, right? So then hardly we get to study like 3 to 4 hours. So in 3 to 4 hours, it become very difficult for us actually. During office timing is we are not, I mean, at least I'm not able to study. I have like almost 10 to 11 hours of work daily. So that
Even before the course started, even before this course started, we asked many coordinators, ma'am, like what are the prerequisites and what are the math concepts that we need to brush up. So
we
they
wasted
themselves
almost
do not
1 month
know.
actually after it.
Yes,
Okay.
yes.
Anyway,
That
I'm giving this
orientation
feedback.
itself was taking like 3 to 4 weeks.
Okay.
Just
So
a
what I have
technology
done,
platform.
understood. Even I'm finding it very difficult. Sometimes you feel that I'm getting annoyed, but for me, what I'm understanding, this is just a ABC what I'm teaching you right now. So if if you don't take the minimum of the algorithms, what is required, you want, I mean, machine learning, when you say you know machine learning, you should know those many algorithms. So understood now, I understood that yes, you are not acquainted with those many maths and all. So we are asking every class, please go through the mathematical concept, calculus and linear algebra. This is based on maths.
There is no way to make our voice heard by the coordinator. So can you please do your end? Like we don't have any option to tell them like
You can write an email to them, but what I
single
have
mail,
given them.
single mail will not help. No, if multiple people are sending the mail, then they will take some action or something.
See, that's what I have suggested them. Probably this batch also I said you can share the recordings of IDS, what we take in the classes, like the other program, and some maths. Even though you're learning maths, let them learn some maths in advance. So that's what I've already shared. They are working on it. From next batch onwards, probably how the Python 0, we are giving code 0 as a Python. This too also will be shared. That's what I've been told. Now, what I can say, what you can do for a quick understanding, Khan Academy is a very good resource. Videos, they are videos, very small videos. So quickly, you don't have time to go through all the literature, right? Or the bigger, larger videos or bigger contents. And the 3 blue, 1 brown. These two are good ones. So when you come to any class, or first just Khan Academy, try to understand linear algebra and derivatives, not integration part. And that too, don't go in the very advanced topics, base topics. And yes, Python. You should know Python well. NumPy, Pandas, and sklearn. sklearn, okay, not so difficult, but yeah, NumPy and Pandas you should know. Okay, so I understand your situation. Yeah, but I think
which you have mentioned that is on YouTube.
yeah, they're freely available. YouTube, freely available. Khan Academy and 3 blue 1. Okay, let me just write it down here. Just writing in the chat, Khan Academy. And what is that? 3? I think it's 3 blue, 1 brown. Something like this. It is 3 blue and brown. It's a YouTube series. You don't have to go through all the YouTube series, but relevant.
For which
These concepts in those two series.
Basic concepts I'm talking about, mathematical concept. When you will open a series, you will come to know. pick up what you want. Now we are studying linear regression. You can only pick up the linear algebra or the partial derivative part of it. So this calculus basic knowledge and is what is needed. So generally what we do when we teach in data science engineering, we actually take a maths refresher one session. But here there is no time for maths refresher. So that's why I suggested to send to give all the students some maths recorded videos. So I'll again remind the coordinators to give you those recorded videos. But for the time being, these two are good resources if you do not get access on time.
Yes, ma'am. So for example, right, for Python, there were some refresher courses. Those were helpful to us.
Helpful. Yeah. That's what I discussed with them also, because I'm sensing this problem at every class. And I told them I'm taking really extra, like when I've not reached to not complete a linear regression, I'm supposed to complete it by today. Every class I'm taking 30, 40 minutes extra. And that too, students are still not satisfied. They are feeling that I'm going very fast. But after like 3 session taking 40 minutes extra, after at the end of four session, I'm not able to complete linear regression. So I've given this feedback because of lack of the prerequisites here. So give them the recorded lectures. That's what I've given them, that feedback. So you can also reiterate, ask them those, you can write an email. If you want, you can write an email to me. I can forward it to their coordinators. Or you can write to them, you can put me in CC, whatever way works for you. But like what I understand, this Khan Academy is sufficient to understand the maths basics. Not to wait for if that thing happens. At least your batch has already started. So quickly you need to come to that maths understanding and the data understanding up to that level. I think data understanding, you are fine. The problem is with the basic mathematics understanding.
Basics of derivatives, basics of vectors, and basics of matrices. These three aren't right? Okay.
Right now, yes. Post mid-semester basics of probability, but I think at that time you would have done a good amount of ISM course.
Right.
Probability and statistics.
That is already in progress.
So that you would have done. So right now you can do this. Basics, matrices, vectors, and vectors, matrices, and linear algebra. Dot product, matrix, multiplication, like that. So you will understand those derivations. Otherwise, you will not understand those derivations. Okay?
Okay, thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, ma'am.